Lecture we were discussing about the decomposition method. Let us discuss what we have done last time. So, we were discussing about the decomposition method. We mentioned that we can use this method for solving the system of equations Ax is equal to b. We can solve this system of equations. Alternately, we can also find the inverse of a matrix for finding the inverse of a given matrix A inverse. Now, for this purpose we had written A as the product of L and U. L is a lower triangular matrix and U is an upper triangular matrix. Now, we have also shown that if you multiply L and U and compare with A, we have got n arbitrary parameters that are there, and hence we said choose either Lii is equal to 1, that is the diagonal elements of L as 1, or we choose Uii as 1, that is all the diagonal elements of U is equal to 1. Then the computation is simplified enormously, because we can just get all the elements of L and U by simple forward substitution if we use this particular way of writing it. Of course, there are other ways, you may think of other ways of writing it, however that will not simplify our computations. Now, let us see how we can implement this in our computations. So, let us take Uii is equal to 1. So, let us take Uii is equal to 1. Therefore, my system of equations A into A is equal to L into U would look like A11, A12, A1n, A21, A22, A2n, An1, An2, Ann. This is our given matrix A. Then I write the product as L11, L21, L22, so on, Ln1, Ln2, Ln. These are all zeros. Then I have here U, we are taking Uii is equal to 1. So, I will put 1 here, U12, U13, U1n, 1, U23, U2n, so on as 1. We have taken all the diagonal elements of U as 1 and we have set up this equation. The procedure in any case is we multiply these two matrices and compare these elements. So, we will say multiply L and U and compare. Interestingly, we can find these elements of L and U in a particular sequence. We will see that we can first find all the elements in the first column of L. So, we can determine all the elements in the first column of L. Now, we multiply the first row of L, first column of U, that is simply L11. So, L11 is equal to A11. So, L11 is equal to A11. Now, I am going through the first column of L. So, I will take the second row multiply by the first column of U. So, this is L21 into 1, remaining are all zeros. So, L21 is A21, L21 is A21. Similarly, so on, I will have the last row multiplied to the first column, Ln1 into 1 will be equal to An1. So, Ln1 is An1. That means, the first column of L is same as the first column of A. So, the first column of L is same as the first column of A. In other words, there is no computation involved here, we just replace the first column of L by the first column of A simply, these are the elements. Then we go to first row of U. So, in the next step I would now proceed on with the first row of U. Now, proceed multiplication to the first row second column L11 into U12, that will be A12, that is L11 U12 is A12, that is let us now solve for U12, U12 is A12 by L11. So, this is U12 is A12 by Ln1. Then I multiply the first row with the third column, that gives me L11 U13, L11 into U13, that is your A13. Therefore, I have U13 is A13 by L11. I proceed on the first row multiplied by the last column, that gives me L11 into U1n is equal to A1n. Therefore, I have U1n is A1n by L11. Therefore, what we have here is U1I is A1I by L11, I is equal to 2 3, so on. In other words, we can say that the first row also can be immediately determined, because the first row of U leaving the first pivot is nothing but A, the elements of A divided by the leading element of A, because L11 we have proved that L11 is A11. Therefore, it is simply division of the elements of U by the leading element A11. Therefore, we can state here the first row of U except first element, except the first element is the first row of A, again except the first element, with a division of the leading element, with a division by the first pivot. That means, what we are saying here that you can take the elements of A, divide each one of these elements by the leading element, that is a pivot, and that will give me all the elements of U11, U12, U13, so on U1n. Now, the first row, first column of L is complete, first row of U is complete. Now, I go to second column of L, second row of U. So, now we go to, now let us find the elements of the second column of L. Second column of L. Now, in order to determine the second column of L, I need to consider the product of the second row of L, second column of U, and so on. Let us first do what we will get here. So, I have here the second row of L is this, and the second column of U is U12, 1, and so on. If I multiply, I would get L21 U12 plus L22 is equal to A22. Therefore, this gives us L22 is A22 minus L21 U12. Now, we have determined this element L22 here. Now, I would take the third row of L and the third row of L and the second column of U. That means, I will now consider the product L31, L32, L33 so on, multiply by U12 1 so on, which gives me L31 U12 plus L32 is equal to A32. Therefore, this gives me L32 is equal to A32 minus L31 U12. Now, we have determined the element L32, that means this element L32 has been determined. Now, let us now take the next row of L and the second column of U. That means, we shall be considering L41, L42, L43, L44 into this second column is U1, 2, 1 so on. If I multiply, I get L41 U12 plus L42 is equal to A42. Therefore, I get L42 is equal to A42 minus L41 U12. Now, from this I can generalize that Li1 in general I can write down from here Li2 is Ai2 minus Li1 U12 I running from 2, 3 so on n. Now, the last element of this column will be obtained by multiplying the last row of L into the second column of U. That means, we are talking of Ln1 U12 plus Ln2 is equal to the element An2. This gives me Ln2 is equal to An2 minus Ln1 U12. Hence, you can see that for obtaining the elements of the second column of L, it is sufficient for me that I use this particular equation, which I would write it again as Li2 is Ai2 minus Li1 U12 I running from 2, 3 so on n. Therefore, in one loop I will be able to get all the elements of the second column of L by just putting the range of the loop from I running to n, then I will be able to determine all the elements of the second column. When once we complete this, we go to the second row of U, second row of U. That means, I would now like to find out what will be the elements of this second row, that is U23 so on up to U2n. Therefore, I now multiply the second row of L and third column of U, which gives me L21 U13 L22 U23 is A23. That is the first element of U, that is your U23 is equal to A23 minus L21 U13 division by L22. So, you can see that the elements of U would again require division by the leading pivot L22. So, that is the leading pivot L22 that is determined in the previous step. Now, we can generalize it and write it as U2j is equal to A2j minus L21 U1j divided by L22 and I going from 3, 4 up to n. Now, I can the entire set that I had written here can now proceed on. We go to the third column of L. We now go to the third column of L, then third row of U and so on. So, this is how we proceed on in the actual computation. Therefore, I can write down what all I have written it again once more. Let me write it. The method therefore is, we start with uii is equal to 1, we start with uii is equal to 1, then I can have Lij is Aij summation, this I will now put it in summation notation, k is equal to 1 to j minus 1 Lik Ukj for all of course I greater than or equal to j, and these elements Uij is Aij minus summation of k is equal to 1 to I minus 1 Lik Ukj and divided by the leading element, diagonal element, that is your Lii, of course all I greater than j. This is the notation in the matrix notation. In the summation notation, we can now write down all the elements of L and U in this particular form, and what all we have written earlier just follows from this one. We have just determined it in this way. Now, as we mentioned earlier, we have your L and your U. When we are computing the elements of this, I am first completing the finding the elements of L first, then I am completing the row of U, then I am completing the second column of L, then I am completing second row of U. So, we proceeding in this particular manner these ones until we reach your last element of your element here, and here the element was already 1. So, we reach the last element of 1. Now, the computer implementation has been made quite effectively. This particular method, as I said, this is one of the most popular methods than even the Gauss elimination method. Various strategies of actually writing the program for the to make the computations optimal has been done. One particular thing is the storage, that is in which you do not have to ask for storages for A, L and U. You can overwrite the elements of A with the elements of L and U. So, that we knowing that the elements uii is equal to 1, we can overwrite the elements of A by the elements of L and U as the computation progresses on. Therefore, we do not need matrices of order n into n for A, n into n for L, n into n for U. So, the optimality can be obtained in the way one can do the storage and the other aspects of the problem. Now, let us now assume that we have now obtained our A is equal to L and U. So, we are now this. Now, the next step is, we have given two problems in the starting is, and that is one to solve your system of equations Ax is equal to b. Now, we substitute for A, that is Lu into x is equal to b. Now, I denote the product u into x is equal to some vector z. Then this reads L into z is equal to b. Then the method, we shall write down the method as solve, we shall solve the first, the second one, Lz is equal to b, then ux is equal to z. Solve first the L into z is equal to b, then solve u into x is equal to z. Now, we know L is lower triangular, therefore, this is forward substitution. So, we are solving this by forward substitution. We are solving this first set of equations using forward substitution, and whereas this is U, the upper triangular matrix, and therefore, this is solved by back substitution. So, I can solve this by back substitution. Therefore, besides the decomposition of A into L into U, I need one forward substitution and one back substitution to get the complete solution of the problem. Obviously, the work or the bulk of the work is in only decomposition of L into U. These are, we can give the exact number of operations that takes place because these are simple forward substitutions. Now, let us see what we would do if I need inverse of a matrix. Now, if I need the inverse of the matrix, so we start with A is equal to L into U. Let us invert both sides, A inverse L into U inverse. So, that is U inverse L inverse, that is U inverse L inverse. Now, we know that L is lower triangular, L is lower triangular, therefore, L inverse is also lower triangular, therefore, L inverse is also lower triangular. Now, what does that imply? If I now I want to find, knowing L, I want to find L inverse. Therefore, I can write down, to find the elements of L inverse, I will use the identity L into L inverse is equal to I. That means, I will write down L11, L21, L22, Ln1, Ln2, Lnn. And then the inverse is to be determined. So, I will call this as Ln1 prime, L21 prime, L22 prime, Ln1 prime, Lnn prime, and this is equal to I, identity matrix. Now, you can see that if I multiply these two, I can get L11 prime, first row first column gives me L11 prime. For example, L11 into L11 prime is 1, we are equating to identity matrix. Therefore, L11 prime is 1 upon L11. Now, I can proceed to find other elements, and you again see this is a forward substitution. So, again by forward substitution I can get all the elements of L. All the elements of L inverse, this is our L inverse, all the elements of L inverse can be determined by simple forward substitution using this. One particular point that can be noted is that this is a lower triangular, therefore, these diagonal elements will be just the inverse of the diagonal elements. That computation we will not really do it, because L11 prime will be 1 upon L11, L22 prime will be 1 upon L22, Lnn prime will be equal to 1 upon Lnn. So, these diagonal elements need not computed, they can just be given the values of this, and then we can proceed on find the other elements all by forward substitution. Now, I need the U inverse. So, again I would start with the concept that U is upper triangular, U is upper triangular, therefore, U inverse is also upper triangular. U inverse is also upper triangular. Now, our U was 1, U12, U1n, 1 U2n, 1. Therefore, its inverse will be 1. I am writing the elements solution of the elements, because if I write U11 prime, I know 1 into U11 prime will be equal to U1. So, I can write down 1 itself, that is U12 prime, U1n prime, 1 U23 prime, U2n prime, so on 1 is equal to I. Now, I have already replaced the elements of this, because there will be the inverse of these elements. So, I have taken 1 1 1 over here, and then now I can work backwards and get all the elements of U. Therefore, the back substitution would give me all the elements of U inverse. Back substitution will give me all the elements of this matrix U inverse. When once we determine this L inverse and U inverse, then we can write down required A inverse as U inverse into L inverse. Now, this can be used to just keep the inverse of the matrix, or it can be used also for finding the solution of the system. If we are solving a system of equations, we can also use this as x is equal to A inverse of B if we need the solution of the equations Ax is equal to B. Now, as given here, we discussed in Gauss elimination also that the pivot is 0 or very small, then the method may fail, as given there. Here also we will have a difficulty if any one of these pivots Lii or Uii, whichever the procedure we are taking, becomes 0. So, it will fail only if Lii is equal to 0, not all, some, or Uii is equal to 0, some of them, then the method fails. But of course, there is always a way out for this one. One can introduce the other techniques of avoiding this pitfall of having a pivot as a 0. However, if the given matrix is positive definite matrix, then none of these LI's will be 0 or UI will be 0 and decomposition is guaranteed. So, if A is positive definite, if A is positive definite, then LU decomposition is guaranteed. We have given the this is all the leading minors are positive, or the leading minors of a matrix is 0, that is the determinant of 1 into 1 is greater than 0, determinant 2 into 2 is greater than 0, and so on. That is a way of testing that it is a positive definite matrix, but this is a sufficient condition, not a necessary condition. So, this is only a sufficient condition, this is a sufficient condition. In the other cases, we would use the other techniques of avoiding this pivot being 0. Let us take first a simple example wherein our procedure may fail. Let us just take that example where it may fail. Let us write the question like this: can the LU decomposition be obtained for the given matrix? Can be obtained for A, let us take it as 1 2 3, I take this as 2 4 1 2 3 1. Now, this is a 3 by 3 matrix. So, let us straight away write down our A is equal to L into U, and again we will take UII is equal to 1. Let us take UII is equal to 1. So, I will have here is L and 1 0 0, L 2 1 0 0, L 2 2 0 0, L 3 1, L 3 2, L 3 3, 1 U 1 2, U 1 3, 1 U 2 3 1. Now, let us just multiply it out and write it here itself. So, let us write it out. This is L 1 1 into L 1 1, L 1 1 U 1 2, L 1 1 U 1 3, that is the first row, L 2 1, L 2 1 U 1 2 plus L 2 2, L 2 1 U 1 3 plus L 2 2 U 2 3, then L 3 1, L31 U12 plus L32, L31 U13, L32 U23 plus L33. Now, this is the product of our L and U, which I would compare with the elements of A. So, I know the L11, the first column is the same, L21 is L21 is 2, L31 is equal to 2. This is your 1 2 2 is 1 2 2. Now, let us determine these two elements. U12 is equal to 2 divided by L11, that is equal to 1. U13 is 3 divided by L11, that is equal to 3. Now, we go to L21, U12 plus L22 is 4. This element L21 U12 plus U22 is 4. So, let us substitute for L21, that is 2, U12 is 1, U12 is 2, sorry, yes, you are right. So, this is 2 plus L22 is equal to 4. Therefore, I get L22 is 0. This pivot being 0 will immediately bring us inconsistency. Now, we can see the how it is give inconsistency. Let us put in the next element L21 U13, L22 U23, that is this element should be equal to 1, that is given there, it should be equal to 1. So, let us substitute the values. L21 is 2, U13 is 3 is equal to 1, L22 is 0. So, it is a inconsistency that is coming here. Of course, in actual computation on a computer it would divide by, because we are doing with hand. So, we are able to see that it is 0 and inconsistent, but in actual practice it is going to take L21 U13 to the right hand side, divide by L22. Therefore, division by 0 comes and overflow the computation would immediately arise. So, the inconsistency would come from such a situation. Now, let me take another example in which we can give the solution of the problem itself. So, let us take this example. Solve x1 plus x2 plus x3 is 1, 4x1 plus 3x2 minus x3 is 6, 3x1 plus 5x2 plus 3x3 is equal to 4 by decomposition method. Now, we would take the help of the just now the previous computation that we have done, that the product of L and U is this. So, we can straight away use this particular matrix and then save some time for rewriting them. We know that the first column of L is same as the first column of A. A is equal to 1 1 1, 4 3 minus 1, 3 5 3, and the right hand side vector B is 1 6 and 4, 1 6 and 4. So, we will go by the first column of L, first column of L. Therefore, this is same as the first column. Therefore, L11 is 1, L21 is 4, L31 is equal to 3. Then I can get the first row of U. The first row of U we said that the elements of A divided by the pivot. Therefore, we will have here U12 is equal to A12 by L11. A12 is 1, L11 is 1, therefore, its ratio is 1. U13 is A13 divided by the pivot. A13 is 1, again pivot is 1. So, I will have this as 1. Then we go to the second column of L. Second column of L. So, that is I would take this element as L21 U12, L21 U12 plus L22, that is this element, and the diagonal element of this is 3. So, the diagonal element of this is 3. So, this is 3. I will now substitute the values of L21, that is 4, U12 is 1, U12 is 1 plus L22 is equal to 3. Therefore, I will have here L22 is equal to minus 1. Then I need the second column. So, the next element of L, the next element of the product is this. So, I will take L31 U12 plus L32. So, I will have L31 U12 plus L32, and this must be 5. Now, let us substitute L31 is 3, U12 is 1 plus L32 is 5. Therefore, L32 is equal to 2. Now, we have completed the second column of U. Therefore, I need second row of U. Now, the second row of U comes from this element, that is L21 U13 plus L22 U23. I am writing L21 U13 plus L22 U23, and that is equal to, in this minus 1 is given to us, minus 1. Now, let us substitute the values of this. L21 is 4, U13 is equal to 1, L22 is minus 1, U23 the element to be determined is minus 1. Therefore, 4 goes to this side, I will have U23 is equal to 5. Now, the second row is complete. Now, we go to third column of L. Now, the third column of L means this is the last element that is to be done, and that gives me this particular element, that is your L31 U13. So, I can write from here, this is L31 U13 L32 U23 plus L33, and this element is given to us as 3. This element is given to us as 3. So, let us substitute the values of these elements that we have over here. This is L31 is 3, U13 is 1. Now, we have L32 is equal to 2 and U23, no, I have taken that. U23 is equal to 5, U23 is 5 plus L33 is equal to 3. Therefore, L33 is equal to minus 10. Therefore, let us write down what is our L and U. 1 0 0 4 3 is these elements, minus 1 0 2 and 10 and U is equal to 1 1 1 1 5 1 0 0. Now, the next step to solve is L into Z is equal to B. L into Z is equal to B. Therefore, let us write down 1 0 0 4 minus 1 0 3 to 10 L 3 minus 10, yes, minus 10 and this is our vector Z1 Z2 Z3. We will write down Z1 Z2 Z3 and B is the right hand sector 1 6 and 4 1 6 and 4. Now, this gives the forward substitution. Therefore, Z1 is equal to 1, Z1 is equal to 1. The second row 4 Z1 minus Z2 is equal to 6, 4 Z1 minus Z2 is equal to 6. Therefore, Z2 is equal to 4 Z1 minus 6, that is equal to minus 2. I have written Z2, this is minus 4 Z with a negative sign I have carried over. So, 4 minus 6, that is equal to minus 2. Then the third row gives you 3 Z1 plus 2 times Z2 minus 10 times Z3 is equal to 4, and I will have minus 10 Z3 is 4 minus 3 Z1 minus 2 Z2. So, that is 4 minus 3 plus 4, that is equal to 5. Therefore, Z3 is equal to minus half. Now, the second step is you have solved Lz is equal to B. Now, the solution comes from Ux is equal to Z, where our U is this matrix that we have just obtained. So, that is your 1 1 1 0 1 5 0 0 1 and the variables are x1 x2 x3 and the value of z that we have obtained, that is 1 minus 2 minus half. Now, back substitution would give us the solution. Therefore, x3 is equal to minus half, that is the last row, this x3 is minus half. Now, I go to the second row, I will have x2 plus 5 times x3 is equal to minus 2. Therefore, I will have 5 x3 is minus 2, sorry, we will have x2 is equal to minus 2 minus 5 x3. So, we will have minus 2 plus 5 by 2. So, this is equal to 1 by 2. Then I go to the first equation, x1 plus x2 plus x3 is equal to 1. Therefore, x1 is 1 minus x2 minus x3. Therefore, we will have 1 plus 2 minus half. 1 plus half minus half, that is equal to 1. Therefore, the solution vector finally is 1 half minus half is our solution vector. So, the solution vector is given by this. So, when once the decomposition of A is done as L into U, then one forward substitution and one back substitution gives us the complete solution of the problem. And a comment here is that the amount of round off error that would accrue here is much less than what it would be in a Gauss elimination procedure. Now, very often when the matrix has some special property, we must be able to use the property of that matrix in order to make the computations optimal. One such property is the symmetric matrix. For example, when you are loading a matrix onto the computer, since it is symmetric, one would like to load only the one part, upper part or the lower part, to economize on the storage spaces also. Therefore, we must be able to use this particular the property of the matrix that it is symmetric. Therefore, the method that we have discussed, decomposition method, we must be able to modify it in order that the computations also will become economical. It is possible for us to take advantage that the given matrix is symmetric, modify the decomposition method further to get a still simpler method for computation for symmetric matrices. That I think we shall discuss it next time.